I'm Alan Sanchez. My role as part of the Office of the CISO of Fortinet is dedicated to EMEA. And my actual content today would be about artificial intelligence. There's a lot of hype in artificial intelligence. Do we deserve that terminology? Is it not an overstatement? I'm not going to go into that. Rather, I will tell you what we are doing, how it works, and try to give you a sense of why we believe first that it deserves this terminology, but moreover, behind that, what can you expect out of it? And how can you include these technologies, these solutions, joined all together into an integrated way, and what sort of service can you concretely expect from artificial intelligence? First of all, do we need it? I think it's a very fair question to ask anytime we task ourselves to spend a moment together. And when we look just at two parameters on these two curves here, one is the volume of the threat. You can see that there has been inflection points and that the orders of magnitudes of the damages here, the red curves highlights the number of records that have been stolen since the 90s. We were coming from 4 million, now over 6 billion records. At the same time, we got a similar growth in the number of ransomware attacks around the world. So volume is great. So just this dimension of volumes give us an idea that, frankly, no human brain, no team can cope with this alone. And in addition to this volume, the sophistication of the threats are increasing big time, and themselves are using algorithms of artificial intelligence to do a couple of things, to send some fake code between elementary components that then will be associated to proceed to malicious operations. And because of this ability to deceive some of the existing components of protection, again, there is the need for getting some help from the machine. And when you see how big, how sophisticated, how frequent, and how devastating these various elements. I'm not going to go into the details of these, but just to mention that there are the trends we see is obviously what we've always seen, like exploiting vulnerabilities a way or another. But we see a new trend of malware that actually are damaging industrial plants and resources with trying not to be visible at all. So it's not the type of attacks that we have with ransomware, where it encrypts your hard disk and then obviously has to tell you it's been encrypted and then suggests a way of recovering. Let's take this opportunity to say don't pay. But it's a different one. It will damage the conditions of working of some industrial equipment so that the end products has a quality that is lower and the brand is damaged. And they can be waiting for years, some of the elementary components, then to create the breach for milliseconds that are enough. And then it goes back to normal. So only that speed, that volume, that intensity, and that sophistication calls from something to help us. Now, recently, we have all worked into new architectures. 100% of us working from home and now gradually coming back to work, which happens to me today. It's my first day in the office after these weeks and weeks of confinement. And all of a sudden, the patterns of the networks, the authentication, the resources are changing and will change back because, for instance, in the case of Europe, not the entire number of employees are working at the same time for physical distanciation reasons. So even some of the baseline learning of what normal looks like, and I will come back on that later on today, are changing. You would be using some resources from one place, then from another place, and both are normal. So this new normal, which is a dynamic use of resources that we have still to modelize, to figure out if we are under attack or if it's just the normal coming back or coming back to the office or coming back home type of activity, all that changes on a very dynamic manner. And only cybersecurity analysts that would be trying to manually correlate some incidents coming from the network and some incidents coming from the security operations center would really struggle to try to refine normal patterns on moving architectures that are dynamically reallocating the use of resources. So we need something to help us just for that first profile of the threat and intensity of the threat. The second thing is perimeter has kept changing and will not stop changing. A couple of things that are related to this phase where we're coming back to work. There will be more and more devices that maybe have been bought for professional reasons by employees that IT could not completely format, but yet due to the necessity of keeping the business going on, maybe some compromise has been made, or at least some new devices, some new softwares, various versions of the OS, all that is coming together gradually. Take the network side of it. 5G is one of the examples, and for two reasons. First of all, 5G is not 4G on steroids. It's not just a better and faster 4G. It's a totally new, distributed, very exciting architecture, but very different. The emergent tip of the iceberg that we get to see today are the antenna. But 5G is not about the antenna. Service providers started by the antenna because it's the easiest way to cash the investment of 5G. But you have the core of 5G, which is a mosaic, a new distributed architecture where elementary services such as billing, isochrony are called upon a bus and associated together in a dynamic manner. Dynamic as well is the slicing you do in the usage of the physical infrastructure and the speed, one order of magnitude. So you have to cope with that. You got to have the insight into the frames and a sophistication of the content, a higher speed. And during that part, the rest of the technology are continuing to evolve as well. So the network is changing, and very quickly, the computing model changes with the cloud, the distribution, the fact that some data centers are hyperscaling, whether or not they sit on one side or the other of the cloud. So all this together, when you look at all the consequence of that, you find yourself in a different universe and in a changing universe. So in that equation, in that world of change, what is IE actually used for nowadays, and how do we use it for? The first one is to learn behavior. Learning behavior enables to detect abnormal usage of resources, even when the resources are accessed through legitimate credentials that might have been stolen. It's like someone steals the keys of your car, and the car starts, and the person starts to use the car. And all of a sudden someone says, well, it doesn't quite look like his way of driving the car. For instance, here, some of the technologies that 40 Insight uses is based off a learning of what normal behavioral is. A normal user, for instance, does not do what a typical malware would do, which is I have access to these resources and I open every single directory that is accessible through these credentials. I looked into all the files, I delete all the backup files. A normal user would not act like that, even if the resources have been accessed with a perfectly legitimate and valid sets of credentials. This doesn't look like the way a normal user would do that. And the way we use that fact is we machine learn by profile what normal behavior is, and we classify the users based on a series of parameters: number of applications, number of communication sessions, obviously physical presence of the IP addresses that are part of the resources, and a couple of other things that becoming the baseline use of a typical user. So that's one element where we use machine learning. We also use it on malware detection. Malware are dropped, as we saw in a previous conference, in phases. There is one phase is when you discover, then one phase where from this discovery you start to put a beachhead of malware, and then you go about invading, right? And as you go about doing that over time, as I said earlier on, the time frame by which the new malware are dropped, activated, deactivated, reassociated, and reactivated changes a lot, right? So you see this new behavior, you see these new elementary components, these new timings, and you got to make sense out of that, because some of these elements can be perfectly legitimate as well. Encryption can be one element of deciding whether the incoming traffic could be a ransomware, because a ransomware actually encrypts. But it can be a very legitimate encryption. It can be one page that is protected. It can be one zip file that has been encrypted. It can be an Excel spreadsheet that has been encrypted. So you have from that to weight properly the contribution of these elementary red flags or orange flags or green flags and make sense out of that. And in that activity as well, artificial intelligence / machine learning is used extensively already to accelerate, to identify, to drop some of the files, to let go some part of the traffic. And same thing for the web traffic analysis, which is perhaps one of the most difficult and most complex activity to be able to spare the normal from the abnormal. And the density of the traffic is such that we're using algorithms that sample, learn from the sample, deduce the scope of the potential risk, and recheck it against some other traffic that has been seen before, right? So we use for that a series of micro gatekeepers, as I call them, that process input files, and each of these little dots that you can see, for instance, here on the first malicious layer here, would try to give a probabilistic value of that fraction of the incoming traffic to be either malicious in the first level. So how does it look like something that has been proven to be malicious a little earlier, is one of the tests that these elementary components are proceeding. And then it would give a value between 0 and 1 to that elementary test. So it pretty looks like something bad. So I put 0.7 in one of these elementary components, and then my little friend down here does the same, either on a different fraction of the incoming traffic, or proceeds to the same on the same fraction of the traffic to another test, etc., etc., etc. And it is compared to something that we know is malicious, or we have just been seen being part of an attack. And it goes to another layer that see, well, yeah, it does look like something bad, but how does it look like something good? And out of these elementary scores, scoring probabilistic numbers that are calculated very fast, comparing an incoming traffic with something we know being good, something we know being bad, it gets out with an overall note, and that note triggers the firewall and does something about it. Something that depends on the actual threshold or the actual value compared to a threshold, and something that also compares the action that has to be taken to the company policy. And you may decide to let go over a certain level of threshold because your company, your ability to take a risk that is tolerable, acceptable for your business is such, or you decide never to take the risk, whether or not it's under a value. So this is how we're using neural networks to assess a number that reflects the actual capacity of an incoming traffic to harm, to damage your organization or your network. A couple of things that you can think about that. The first question that I think comes to your mind when you say that is, okay, so it's a bunch of tests. Okay, that's what it is. A bunch of comparison tests. Where does that deserve the I? Where is that intelligence? Because it's Boolean logic. It's and or if and then and nor, etc. Along the way, we've been doing that for 40 years, right? Maybe not that fast, but directionally, even Alan Turing in 1920 already set the basis of an approach like that. He didn't have the same computing power. So where is the intelligence here? The intelligence is in the ability to weight and re-weight dynamically the importance that you grant to some of these elementary tests. In other words, when you go about doing the sums in columns and then at the end of the two columns, you would affect with a certain importance some elements of the tests because they have been seen involved in something either perfectly malicious or perfectly clean, even in the couple of hours or minutes before the test was done. In other words, what would have been let go only 3 hours ago now triggers a super segmentation or a drop of the frame or an isolation of the IP or a certain IP range, and that is dynamically reassessed based on what we have seen before, and the before can be minutes before. So you reweight the elementary component and the elementary tests that are part of this assessment of probability, and then you earn the I of artificial intelligence because it's been done according to something that has been proven to be right or has been proven to be wrong. Then you learn. Then this network of neurons, so to call them, they are actually not, biological neurons, but logical neurons. And they don't have yet the power of calculation of a brain. So there is just an analogy that we're doing here. However, they learn. So the prediction gets better and better as we go about comparing the overall assessment of the probability of an attack to a base of knowledge that is dynamic and evolving. This is how we believe it earns its ability to learn, and then the ability to be called intelligent. This combination of multiple layers, elementary nodes, features, and ability to take into account the very recent past based on the actual damage that something like the traffic that we are analyzing now is doing. This is where we end when the accuracy, of course. The ultimate verdict is, do we do the job properly, right? And as the accuracy gets better and the proper weight is affected dynamically to all these elementary tests, yes, we can call that machine learning. The principle being that you have this incoming file, you calculate the probability of that to be bad, you reassess that in another layer and comparing to the probability that is good. Back to what I was saying, there is encryption. Encryption is generally not very good, but when associated with that specific line, that it's actually the equivalent, the behavioral equivalent of what is normally used in an Excel spreadsheet file, you can call this encryption legitimate and you assess a result. But if there was a malware that only minutes ago in some other part of the world or your organization was actually using these elementary components and turned them into probability, the weight that you would be given in the second layer would be higher, and you will have a result that would actually get rid of this frame, whereas it was perfectly okay to let it go only an hour ago. So when you multiply that and you have the proper level of calculation power to turn this series of features across a vast range of elementary tests, then you get a result that not only reflects the actual probability of the traffic to be harmful, but that evolves over time a lot faster than a human analyst could do. Because if I was basing that on my own experience, I would perhaps take a decision that is based on something I saw 2 years ago, and I will create many false negatives, because I would call that, no, this is okay. I saw it before, it was actually not something that was part of a malicious attack, but it's been recently proven and recently seen as a fact that this algorithm is actually currently used for a malware, and it's not a false negative, it's actually a positive, and we have to do something about it, right? So these are, for instance, some of the way we are actually using that approach that I described. So let's say a ransomware, something that goes about, for those of you that can read that, about opening every single directory of every single accessible resources is already something not really normal, right? But then you open all the directories, you open all the files, you start to detect that even if it's later or not even done yet, you have a sequence that deletes the shadows copy. That cannot be completely okay, right? And then you allocate that, but you do compare that with other tests, and you do compare that to the history, and you do tap into your knowledge base, and then you have this kind of graduation in the sophistication of the defense, where you're not only looking into the bits and bytes, you're starting to look at the way the bits and bytes are associated, even if it's at a later time frame. And the time frame could be 3 machine cycles or 3 months, right? It doesn't really matter for that sort of technology. We'll still remember it. you see the way he behaves, and we see the actual effect that it has, and you compare it, right? And then you have a scenario-based artificial intelligence algorithms. And the way you teach that machine is you would send sample to these neural networks, and you would know initially whether this sample would be harmful or legitimate. You would look at the way it's classified by the system, and you would actually start to enhance your ability to classify between malicious and clean. And then you have a permanent accuracy, and the system gets better as it goes. So you have this theoretical curve at the bottom left, where you see this arrow that grows, 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 and then reaches a level of quality. Now it's true directionally, but it can take 24 to 50 weeks on a complex network for a machine learning algorithm to be able to very accurately spare the good from the bad based on the overall behavior and use of the network, right? So yes, it learns fast. And after a certain period of time, it gets actually better than a human analyst, and offload the team with some of the very repetitive tasks that are involved into that process. But don't believe it's instant, right? Machine learns, but machine takes some time to learn. Another reason why we say this deserves the eye, the intelligent why, is the database of experience into which it taps is permanently updated. As I said, there are some trends in cyber attacks. There are some elementary components that have made available and that will be associated in a different way, and that evolves over time. And so that enormous footprint where you can compare, and by the way, some of the logos here are here for one reason. It says, when we learn that something is part of something harmful, we share it. And when we say we, it's about the 6 million of firewalls that we have installed around the world, plus the information that is incoming from our competition. So we share that. We say that combination, that association, that sequence has been proven to be bad. So we upload it into a platform, and that platform is made available throughout the entire community of users. So that ability to tap into a big knowledge database that is permanently updated is also part of the sophistication of the reweighting process that I was describing before. And the way it works is quite interesting, because it works the same way a real analyst would actually work. So to me, that is one of the differences of Fortinet artificial intelligence algorithms compared to competition. It's not something that starts with artificial intelligence algorithms that are found and then applied back on cybersecurity process flow or problems. It's the way we have learned all that, the way we used to do it, amplified, magnified, sophisticated by the power of calculation and the density of the neural networks, and the ability to tap back into what we know has been detected as bad, proven as bad, right? So the way it looks like, when you look at your FortiAI dashboards, for instance, here, you can see on the left-hand side the different types of malware that are classified. And the fact that is red, amber, green here, or blue, amber, red here, depends on your own capability, willingness to take some level of risks, or your own traffic. So it's dynamical. It's not one size fits all. right? And you see, for instance, that there's a warm activity with an IP address. Here, you would click on this IP address where it's grouped by attack scenario. You would have the IP infected, which is a very crucial information, because you know that, for instance, in a range, what is before can be considered as clean, so you can maintain the activity there. And what is further than that in the IP range has to be dealt with. And then you have a sort of cartography, a map of the spreading by nature of the worm, and you can do lots of things with that. You can trigger the response in the good order. You can actually explain what's happening, and you have to do that internally for the sake of people being more effective in detecting it. But sometimes you have to do it externally, because you have to explain in the eyes of the law that you are actually doing something about it. And that sort of ability to say, we know where it started, we know how it spread, we're on it, we're doing that, is actually very useful for your image as a company, because the CISO is more involved in external communication, but also more pragmatically to the fine that might be infliged to yourself. Because when you can prove you're doing something about it, the orders of magnitude of how much you can be fined as a company are totally different. You get fined at the highest level when obviously you don't do anything about it. You just log that there was a problem. Here you can have a roadmap of de-infection, or a roadmap of addressing the problem, or releases the vulnerabilities. You're in a totally different standpoint when you have to explain that to your board, to your internal users, to an audit team, or to a government entity. So the way it works here, as you have understood, is you can trace the spread of the worm in that particular instance, and you understand how it goes about spreading, and you know what part of the resources have to be dealt with. So I was mentioning earlier, yes, it learns, right? It's not instant learning. Here you can see in amber, in orange here, the actual performance of the machine, and in blue you have the actual performance of a trained team to be able to detect. And you can see that, yes, it gets better, and there's lots of stress that it takes out, but it's not instant. In that particular case, it's about 32 weeks, because the patterns, and particularly now as we're coming back to work, I was mentioning these moving patterns, we have awkward patterns compared to everyone in remote, or everyone working in the office. So the machine has to learn that. The machine has to be able to say, yeah, okay, this particular profile used to connect from that range of IP address, but 3 days a week, it's absolutely normal that it connects from this other place. So we don't have to raise a flag here and send a false positive somewhere else. So this is just giving an order of magnitude of how long it takes, right? So the way also we do that, we're able to analyze the behavior of users, is we using a 3-layer architecture, and we start by collecting information anywhere. This is why it takes a bit of time to learn it, and whether it's centralized or decentralized, we would profile data usage company by company. So this is a typology, a typical typology, but obviously, and I've represented here 3 parameters that are part of the learning methods. The number of systems used vary from a profile of someone who is a programmer, someone that works typically in a financial department, or someone more senior working in the HR department. You can see that typically the number of systems being used, the number of network connection, the number of simultaneous application use changes. So even if someone would steal, for instance, the credential of Mr. Pete, at the bottom, and all of a sudden would have a number of network connections that are way above. And again, here I have only represented 3 parameters, but we track about 40 of these. The correlation between the profile of the person that has been dynamically learned, the actual usage, the geolocalization, the type of process, the type of transfer, the duration of transfer, all that sort of gives a behavioral signature. Signature is a bad word here because in antivirus, a signature is an hashtag that you apply and recognize from the outside. Here it's a behavior that you've learned from the inside. But I think you know what I mean. The typical way of Mr. Pitt to go about using the network is weird. And then you can decide what to do with that abnormal activity coming from normal credentials and profile people and better protect you, even when the threat is very sophisticated, because it's actually not only the bits and bytes of the threat that you monitor, but also the way people go about using it. And I'm coming back here on something that is very important, right? It's even when you, as it's done here, you have cataloged week after week the usage in terms of login times, working hours, open processes, and again, there's many more parameters than that we track, and compare the actual usage of these various. It's an indication, right? It's part of what you do to assess whether you're under attack. But you have also to associate that with other technologies. And one of them is the web traffic analysis, right? So just to remember, web traffic analysis used to work by comparing a list of what is authorized or weird or unauthorized with an actual traffic. And sometimes it does look like that, sometimes it doesn't look like that. And you would, at the end of this filtering process, recuperate all the anomaly. And because it's flagged as an anomaly, it would be blocked. And by doing that, you block a lot of legitimate traffic. And you have customer internal user satisfaction that drops. And some of the traffic that is allowed, which is even more important, the first one is not good for an image, for your image as a CISO. The second thing is not good for your organization. You can let go some part of the traffic because just they were not in your whitelist to start with, right? So the way we do that is we enhance significantly that web filtering process is by applying 2 layers. One of them is a statistical probability to look like something that is in the whitelist, which is already a great enhancement compared to it, right? And then you go to another layer where you have pattern analysis about what it does and taps into a tank of behavioral analysis of web usage. And then you have a far better ability, and you can re-inject in this second stage some of the traffic that you would have forbid in the third place. So you end up having a far better ability to understand, insight, have some proper statistics, and then usage of it, right? So again, here, it's the combination of the ability to smartly filter and the ability to learn what normal is. You can find yourself in a particular activity where that kind of traffic that you would have forbid on a trading floor in a bank is perfectly legitimate, is actually part of the business that the company is making. So you have to learn that, and you have to have something that is sophisticated and integrate the machine learning algorithm into this web filtering activity. And we've been doing that for already 9 years. We have an experience of processing a huge number of queries every day, because by the same time, the sophistication of the protection algorithm has really benefit from artificial intelligence. The computing power we have now is a lot higher than it used to be 9 years ago. So as a net result, not us, independent entities have tested and have detected a detection rate that is over 99%, which is frankly a great enhancement. So let me just close on saying something. We've talked about artificial intelligence in 3 different dimensions, and we saw how it worked and why it deserves this little eye. But it's never a panacea. It has to be surrendered by a series of defense that put that in perspective and allow you a holistic protection of your incoming traffic. One of them is the merger of security and networking domains, right? Look at the success of SD-WAN at the moment. SD-WAN is a pure network, as I said in my previous conference here. It's a pure network concept. You and the application tells the router to do things. That's pure networking, right? But adding security into that requires that you actually put that in perspective with another sets of activities. Zero trust is any user, any application, any devices, any IP range is not by default authorized. It has to earn, compared to a profile, a level of risk, and a company policy every single time it's been seen the ability to cross, to use the network. It has to happen any side of the cloud you end up with and that's what we call dynamic cloud security. It's not because you have the opportunity to host, to have software as a service, and any of the greatness that the cloud enables, that you have to change your security policy. Your security policy should transcend your cloud architecture, whether it's cloud native, cloud hybrid, multi-cloud, or no cloud at all. You should not be manually redefining the rules that we've talked about, whether or not you stand one side or the other of a cloud architecture. And we've saw today the importance of artificial intelligence into that equation, but it's not a panacea. It's something that has to be integrated in this holistic approach that we call. And holistic approach does not mean monopolistic approach. One of the key elements of Fortinet Security Fabric is its openness. We've been adopting open standards from the very beginning. Actually, every great thing that happen in IT comes from openness, right? And it does not vary. The feature, the functionality, the code, the algorithm that I just described do not vary whether or not you have an appliance, you have a virtual machine, you have a hosted software as a service, you work into the cloud, or you are in a container architecture, right? So 3 takeaways. One of them, it's because there is this dynamical ability to learn and to relearn and to reassess that, yes, there is artificial intelligence in cybersecurity. It's very useful, and Fortinet has been using for the last 9 years. It does already deliver that value in the 3 domains that we saw: behavior modeling, malware detection, and the ability to smartly scrutinize something as complex as web traffic. And it's only good when it's part of a whole. It's never something that, oh yeah, I got this device that does market intelligence, I'm off the hook. It's never like that. It's always a combination of all that all together that makes great security.